So it's my pleasure to introduce Yong-Zhong. Those of you who don't know him, he is a theoretical astrophysicist, works on a variety of subjects, from everything from cosmology to core collapse supernovae and neutrino flavor physics and nucleosynthesis. And these talks, I think, will be more kind of physical seat of the pants kind of thing.
Right.
You know, Yong is kind of an analytic theorist, but he also does computational stuff. But this will give you a lot of physical insight, I think. Well, I think what you're talking about today, into what will come a little bit later with the flavor transformation work, and I think will be a good lead-in to the Big Bang nucleosynthesis talks we'll have next week, and also the flavor transformation talks, right? And chemical evolution and galaxy formation.
Right. So thanks a lot again, George, for inviting me to give this set of lectures here. It's always a pleasure for me to see the young people. You see, my name is something like young, but I don't feel young anymore. So, all right. So as George said, my emphasis tend to be a bit more analytic and try to focus more about connections with what you can observe. So, you can compute away all the way you want. Tony also emphasized in his lectures, ultimately the judge is nature, right? We get graded by Mother Nature, all right? So in three lectures, I will be covering three different emphases. So today, I'm just going to give you the connection between neutrinos and supernova nucleosynthesis. And tomorrow, I will more focused on the nucleosynthesis part itself, especially about the particular kind of nucleosynthesis which are responsible for the bulk of these heavy elements beyond iron, our process. And the last day, I will try to tell you a bit about how we then put all the knowledge we have about how we think these elements are being made in supernova and in other type of stars. And then these stars reside in galaxies, and the galaxy, as we heard from Joe at the first lecture, how galaxy formed during the evolution of the universe, how all this thing gets put together so we have a grand show to understand and appreciate. To start off, I wanted to make a distinction. I mean, so far, I think perhaps this is the first time you heard about type 1 supernova in this lecture, this set of setting, all right? So I'm going to distinguish that we are not talking about this type of supernova. It's a very famous supernova because it made one of our UC colleagues, Saul Perlmutter, being a Nobel laureate, right? The type 1A supernova was used as something called a standard candle. And you use that to measure basically where the supernova occurred, how far it away based on our understanding of these type of objects, and measure its redshift. You can calibrate the distance redshift relationship. From that, you can learn a lot about cosmology. And so this essentially is sort of the sexiest topics in modern-day cosmology right now. But to me, let me tell you how I think about it. It's a grand achievement of many branches of science coming together to give us this grand cosmology. But if you really think about it, what it does is that provide us with a stage. The universe has set up a stage for different things to be played out on it. The cosmology is just a stage, all right? The most interesting thing which actually happens on the stage haven't been shown up on this plot yet, right? But you actually use the one of the player to understand this stage a bit better. And this player is the type 1A supernova. How it happens is that we know that some of the stars, after they die, they leave behind a core, which is called a white dwarf. And the white dwarf has, as Tony also mentioned, has an upper mass limit to be stable, which is 1.4 solar mass or so. And just like human beings, stars don't like to be lonely. Most of the stars actually happen in binaries. Right? So if you have a slightly more massive guy already evolved and became a white dwarf, and it still has a lower mass companion, and as the companion actually evolves to its later stages, it puffs up. And now the gravity of this guy itself is no longer strong enough to hold on to its gas. The white dwarf becomes a grabber of the gas, and now you can see the white dwarf gas can increase. As the mass upper limit is 1.4 solar mass to be stable, and this particular configuration actually become unstable. Now, this kind of white dwarf is pretty unique in the sense that its composition is still quite kind of how do I say that, potent fuel, because mostly it's carbon oxygen. You still can burn it. And when you pile up mass on top of it, it heats up. And so you burn carbon, oxygen explosively, it just blows up, okay? And because original thinking was that you always reach this limit of 1 pound of a solar mass before you can ignite the fuel. So it's a pretty unique number, right? It's a threshold thing. So you think that somehow when this guy blow up, most of the fuel gets burned into ion group nuclei. That's the energy source. So you have a total power output sort of pretty well defined. And that, if you know that you know the power output, that's the luminosity, you observe its brightness, that factors in the distance thing in here. So from the luminosity, from the observed brightness, you can calibrate the distance to that supernova, right? Then you look at the light curve, the optical emission. If you are lucky, you see the spectroscopy, and you figure out the redshift. That's how you calibrate the redshift, the distance relationship. And then you look in the cosmology, then you can figure out all the parameters, all right? So that's how it works. But here's a question for you. We say that 1.4 solar mass is a magic number. How stable, you can have a massive white dwarf to be. This happens in this context. It ends up in explosion, right? In the other context, which Tony talked about, remember, you have an ion core, and it's eventually supported by electron degeneracy pressure. Christian Art also told you about that. That this degeneracy pressure is the dominant form of pressure supporting the ion core at the end of a massive star. And as you pile up silicon burning material, silicon burns into iron on top of it. So you add mass onto the ion core, you push it beyond 1.4 solar mass. What happened in that context? It didn't blow up like that, right? It just collapses. See? 1.4 enters in different contexts and have different outcomes. So these are the interesting things for you to think about. The zero sort you already know. The difference between an ion core and a carbon oxygen white dwarf, both at the limit of 1 pound of solar mass, they have a different fate. One difference is that carbon oxygen white dwarf has fresh fuel. It's a potent source of energy for nuclear burning. Iron, on the other hand, is ashes of the ashes. You can no longer get energy out of it by burn iron, right? So that's one thing. But there's other issues I will talk about later. But here is just the set of the stage. Really literally, set of the stage. So the stage, we know it's a lambda CDM, right? And Joe told us how that under the action of the dark matter, you would have these potentials built up by clustering of these dark matter. And the teeny little bit of the baryons will fall into these potentials. And eventually these baryons cluster together, become stars, right? So you have a stage, you want to put on a show, the main players are the stars, right? So let's talk about these stars of the play. So you basically have this baryonic gas under its gravity, and obviously it also have lots of interesting atomic and molecular physics, because as you collapse under your own gravity, you heats up. And if that heat cannot be got rid of, it just hold you in equilibrium. You cannot collapse any further, so you have to cool, right? You cool down, eventually you become stars. And these stars come in varieties. Again, just like a human being. Look on the Earth. There are small people, big people, more heavy ones, and the lighter ones, right? So the lighter guys, like our sun, is an average star. And it evolves eventually, as I said, it became a white dwarf in the center. The reason for that is that this type of star, as I'll talk about, cannot cook the fuel all the way to iron. It can only go to carbon oxygen, all right? And then it ejects the envelope in some sort of form of wind, and it's called a planetary nebulae, and what you're left with is a white dwarf. Again, being a physicist, sometimes you have to be two other kind of characters in life. One is a legalistic scholar, like a lawyer. The other one is like a poet. A poet is that allow you to have the imagination and creativity. Legalistic scholars that you have to really understand what you're talking about. Say, what about a white dwarf? You say, being poetic, okay, Snow White and seven dwarfs, that's white dwarf, right? Okay, but legalistically, you have to say, why do you call the sky white? Or why do you call it a dwarf? Yes? Okay, you see how it comes about. Because a star, it burns stuff, right? In order to burn nuclear fuels, you have to be hot. And initially, you burn hydrogen to helium. There's some temperatures about kilovolts also, 10 to the 7 degrees. After you burn hydrogen to helium in the core, you have to burn helium into carbon and oxygen. And you need a higher temperature, right? When temperature goes high, the color changes. So you say, how hot is it? It's white hot, yes? Because in order to achieve that temperature, as we will see later, you have to squeeze the star. So initially, the core is of a certain size. In order to raise the temperature to burn helium into carbon and oxygen, the core squeezes. It becomes much smaller. So it's now a dwarf. And when you lift off the envelope, what you exposed as a white dwarf. So being a lawyer and a poet. Okay. So this is how you end up spend your life as a regular star like the sun. You end up with a white dwarf. And you happen to have a companion, right? You are not lonely. Then you can go live your second life as a type 1a supernova, which we just talked about. Now, if you are a massive star, then you are able to repeat this process that you burn nuclear fuel and you sort of stabilize for a while. And then after you run out of the fuel in the center, you have to squeeze, right, contract, and you raise the temperature, you burn the next stage of fuel, all the way until you have iron in the center. By that time, obviously, iron no longer can be burned anymore, so you collapse. And that's the supernova what Tony and Christian are talked about, all right? And the remnant from this process is either a neutron star, in the case of a very successful supernova, or a black hole. But a black hole does not signify a total failure either. It also can be a somewhat successful supernova, but in a different way. And again, if you happen to have these massive stars in a binary, these neutron stars and the black holes can have a second life. That's what the compact mergers were about. You have two neutron stars, two black holes, or a neutron star and a black hole in a binary. Then they are very strongly gravitating, and just like any gravitational system, on the long term, you always worry about the tiny effects, like how much energy you are losing because you have gravitational radiation, right? So initially, you have two compact objects. They're just happily dancing around each other. But think about the universe is more than 10 billion years old. Over that time scale, a lot of things can happen. One thing is that these small energy loss because of gravitational radiation eventually will make the orbit of these guys go closer and closer. And when you get closer and closer, you no longer can view these objects as point particles anymore. Just like the Earth and the Moon system, if you treat it as point particle, not much interesting happens. But if you look Earth and the Moon as bigger objects, the thing you need to understand is the tides. Here's the ocean. Go see it. Tides, right? Because it's not a point particle. Oh, it's the other direction. All right. See, my sense of direction is totally screwed. Anyway, so nevertheless, you understand that. So the tidal force becomes more and more important as these guys get closer and closer. So eventually, you can imagine that the massive guy will be more damaging. It'll rip the other guy apart, right? And this piece of material, if you happen to be a neutron star, suddenly becomes a very interesting place to make interesting nucleosynthesis, because suddenly you release lots of neutrons, right? This I will talk about a bit later when I do the up-process nucleosynthesis. And Dan Qian, he will specifically more talk about the process of these merger things. And I think Christian perhaps will also talk about that as well in a dynamical way, how to model these things. So this is essentially, you think about on the stage of the universe set up by this lambda CDM cosmology. You look at the baryonic players. They show up on the stage as these stars. Their life stories are more or less in here, right? So now, that story is pretty bland in the sense that if you read astronomy textbooks 101, that's pretty much the story you get, right? Except with some modern flavors of lambda CDM and things like that. You want to be a bit more classy. I want a plot which is more interesting. So you go to some higher authority. You say, what is a good storyline to satisfy the scientific public these days, right? Well, you look at it, every decade or so, the US National Academy, they have some policy kind of issues to deal with. Say, like, what are the science agendas we have to fund as priorities. And at the turn of the century, they put out this kind of a document telling you that what are the biggest questions which we're supposed to answer in the new century. And the theme there is connecting quarks and the cosmos. Obviously, you say this is nothing new. Ever since the Greeks, we have been trying to do that, right? Try to understand the most basic constituents of the universe and how they relate to the real universe we see with eyes, right? And they listed about 11 of these questions, okay? I won't be able to obviously talk all these 11s, but 2 of them stand out, and that explains why we are talking about the neutrinos and the supernova nucleosynthesis here. So 2 of these 11 questions supposed to be the biggest to be answered in this century, connecting quarks and the cosmos are, what are the masses of neutrinos and how have they shaped the evolution of the universe? Right? You understand that's one of the major questions. And we have learned a lot about neutrino physics because so far these are the only ones showing signs of physics beyond the standard particle physics model, right? In the particle physics model, which is in the standard version, you don't talk about neutrino mass, as Alex Friedland and Huayu Duan talked about yesterday. So neutrino have mass, then they have some interesting new physics on top of the regular weak interaction. And if they have mass, then they gotta respond to gravity. And so gravity sets up the stage, right? So gotta be some cosmologically interesting thing happens, having something to do with neutrinos, okay? This I won't be able to talk too much about because the oscillation part, Huayu and Alex would be, and other people will talk about more specifically how to model these things. But I will tell you how they might affect other things in the supernova process, okay? And in terms of a massive neutrino, how it will affect the structure formation in the universe, I won't be able to talk about at all. I hope somebody else will cover some of that. The next question among the list is how were the elements from iron to uranium made? Okay? Again, in Astronomy 101, those sort of textbook version things, as if everything is known, right? Now this still is one of the top questions to be answered in the new century. Now if you look at the list, you say this is like a laundry list. Where is the connection? Okay, it's got to be a lousy play. Okay, how are you going to write a play on the stage with these laundry list of questions? So to get your mind at ease, I immediately gave you the answer, the punchline. Why there are connections, the intrinsic connections between these 2 seemingly wide set apart questions. How do neutrinos have anything to do with elements? Again, try to be a lawyer. The lawyer, the first thing they do is they collect data, right? You want to win your case, you just read lots of material, background material about the case. You say, if I'm thinking about nucleosynthesis, the first thing I want to know is what are the products of nucleosynthesis? How have they changed over the history of the universe? Then I might be able to see somehow there is a connection to other things. So here are 2 basic facts. I will mention a bit about the Big Bang in tomorrow's lecture as a standard way of thinking about nucleosynthesis. We know during the evolution of the universe in the very first stage, things were very hot, and you're expanding, you're cooling down. So initially, you just have free neutrons and protons. Eventually, as things cool down, neutrons, protons can no longer stay free. You combine into heavier stuff like helium-4. And the end result of that process, the Big Bang nucleosynthesis, is well known because you can see it in the sky literally. Not on the solar system scale, but a bit bigger than the solar system. In the solar system, the biggest object is the sun, right? You already know that in the sun, we have about a little bit less than 71% by mass in terms of hydrogen, and a bit more than 27% of in mass in helium, okay? And the rest of it, beyond the helium, is the entire periodic table, right? But we sum them up, we call them, these are called the metals, and they make up less than 2% of the mass, okay? So that's what the sun had today, okay, when it was formed. Basically, that's the inventory now. But if you look beyond the solar system, into other parts of the Milky Way, and you look at it, those stars look very old, and their abundance is no longer 71% of hydrogen 27% of helium anymore. And especially you look at the oldest objects, you find that their helium tend to be only 25%. And the rest of it is obviously hydrogen, 75%. And anything beyond the helium is very little. Okay? We now are able to see stars with anything beyond the helium coming up to be less than about 10 to the minus 3, less than 1,000th of the solar value. Okay? Basically, in the size of 2%. So in those stars, everything beyond helium is less than 10 to the minus 5 in terms of mass fraction. So those are very old stuff, all right? So we observationally know what the Big Bang had done. Basically, they gave us 75% of hydrogen and 25% of helium by mass, okay? And we can also do theoretical work. That's the first big success about nucleosynthesis, is that you are able to predict what the universe has prepared for chemical evolution and initial state in terms of hydrogen and helium in this way. So those are the basic facts. The lawyer would dispatch some legal assistants to gather this for him. But now the lawyer comes into thinking, what is this data telling me? 75% of hydrogen, 25% of helium, versus when the sun formed, things change like that, right? What these bland numbers are telling me. What are these numbers telling you? Hydrogen is going down, helium is going up, as well as anything beyond the helium, right? Well, that's interesting. What does that say about the nucleosynthesis in terms of a microscopic way? You say every nucleus is in the form of a combination of a hydrogen, but not hydrogen, just proton and neutron, right? The proton is just proton, nothing else. Anything beyond hydrogen, you always have to put proton and neutron together. They have the same amount of mass, so mass is conserved. A better way to say it is the baryon number is conserved. The total number of neutrons and protons is conserved in the nucleus, right? No matter how you're going to do this nucleosynthesis, the baryon number is conserved. But in order to achieve increasing helium, decreasing hydrogen or proton, you must be able to do what? The total baryon number is conserved, right? And so you are basically turning protons into neutrons. Oh, there you go. Your lawyer thinking kicks. What is able to do that job, making protons into neutrons? You say there are 4 interactions, basics. Gravitation has nothing to do with these fundamental particles. Electromagnetic interaction is not able to turn protons into neutrons. Strong interactions are not able to do that either. So the only way to turn protons into neutrons is the weak interaction. There you go. What happens in the weak interaction? You say, I have a proton in the nucleus in this case. Free protons don't decay, right? Everybody knows this. That's why I put quotes on it. You want to turn a proton into a neutron. First of all, charge conservation say you have to produce a positron. Then lepton number conservation say that the positron has to be balanced by an electron neutrino. See? In order to make anything beyond the helium, or even beyond the hydrogen, you've got to be able to juggle neutrons and protons around and turn one of them into each other. So the only way to do that is by weak interaction. And the weak interaction, neutrinos have to be there. This is a one-liner telling you that neutrino determines the chemical evolution of the universe. Okay? That's pretty good punchline, right? So now we have a play. Before we go on, again, I want to be very particular about these details about abundances. Round numbers are like that in the sun. But you look in detail, hydrogen, helium is way up over here. And there are lots of structure in this abundance distribution of all the isotopes or the nuclei in the solar system. The first kind of feature you notice is that in general, the trend is that as you go heavier, the abundance just drop off like a rock, right? And that obviously you could say that, okay, being poetic at this point, you know, why hydrogen and helium are very much high up there? You say because we all have the common origin. The hot Big Bang prepared the initial state for everybody, right? Even though stars are able to change, hydrogen and helium into other kind of elements. But those kind of processes are pretty slow. Yes, a star life is very long. Even a massive star, lives more than 10 million years or so, right? So things going on pretty slowly inside of the universe. So even though the sun has substantially changed its composition by the time it formed, composition, I shouldn't say it changed, but when it was formed, the composition it received is already quite different from the Big Bang, but it wasn't too much, quantitatively, it's not a hell lot of difference between Big Bang hydrogen and helium composition versus what you had in the sun. But nevertheless, it changed. This kind of a slow change reflects, obviously, partly the weak interaction is not an efficient one, right? And next of all, because any kind of heavier guys, you always got to need more and more neutrons. The reason? Very simple. If you have a nucleus being in the heavier regime, you have lots of protons. If you only have protons, protons repel each other. You want to bind them together, you have to throw in the neutrons, right? So as you go to heavier and heavier guys, you need more and more neutrons. And that tells you it's a very hard thing to have neutrons because it involves a weak interaction. As you go to heavier and heavier guys, you need more and more neutrons. Because of the difficulty of getting the neutrons, the way to make them becomes more and more difficult, so you have fewer and fewer of them, right? Yes?
Just a quick question.
Yes.
What's the axis?
Oh yeah, I should say that. The y-axis is some sort of relative scale, logarithmic, about abundances. So this telling you that the hydrogen and the helium are the most abundant one, right?
So what's 1? Like what would it be?
1 over here is some arbitrary scale. You think about it in this way.
It isn't to a specific nuclide?
No, in this case, it's just the relative. So all you claim here is that, say, I'm setting, say, hydrogen around 10 to the, say, 11 or something, but it corresponds to 71% by mass, right? So it's a relative scale. So it's a more interesting thing to think about. There's about 12 orders of magnitude difference in the abundances, all right? So these guys you understand, because it's a lot easy to get neutrons, and therefore the abundance trend is that it decreases as a function of the mass number, if you want it. The other thing is that these local structures, for example, from hydrogen and helium, they are most abundant after BBN. Then suddenly the lithium barium boron, it's a valley. You just bottomed out, right? They are orders of magnitude low from those guys. And as you perhaps already know, lithium was cooked in some fraction in the Big Bang as well, okay? Quite a bit of lithium in the old stars actually was from the Big Bang altogether. But why these guys are so few? That's also understandable. If you try to look at these guys' binding energies, for example, you find out that they are extremely fragile, okay? And in principle, these guys, if they happen to be in stellar interior at a high enough temperature, a bit more than a few million degrees or so, they get burned up easily. But it's awfully hard to make them, simply because at higher temperature, they burn rather than actually being made, right? So these guys have very hard time to be made. They have a lot of chances to be destroyed. That's the reason why, okay? And we'll talk about, again, somehow there got to be some interesting way to make them. But you already got into a tight spot. You can't do it inside the stellar interior. So where are you going to do it? You say, find a cool place. Huh? Like what, a bar? A cool place. Okay. So you want to find a cool place. Where are the cool places? You say there are two things. One is you're totally out of a star. You go into the interstellar medium, right? There, the temperature is only 10 to the 4, 10 to the 5 degrees. So 1,000,000 degrees, you start to burn them. Interstellar medium is cool. And besides, interstellar medium, the density is very low, right? In order to do destruction, you at least have another agent which will destroy you. The density matters. If you go into a very dilute medium, the chance for you to encounter an assassin is very low, right? So you can survive there. But you are able to be produced in some way because you can have these energetic cosmic ray particles zooming around. And if you notice that these guys, they are at the valley between hydrogen, helium, and the carbon, nitrogen, oxygen, right? So if I have lots of carbon, oxygen, because those guys are pretty abundantly made, and they will be available in the interstellar medium as well. Suppose some particles energetic enough, just zoom by, knock some particles out of carbon, nitrogen, oxygen, what do they become? You say, well, they become smaller pieces like lithium, beryllium, and boron. So that's one way of making it. Okay? What that got to do with neutrinos? Because in order to get these high energy particles zooming around in the interstellar medium, you got to have a way to accelerate them. Yes? And how do you accelerate particles? You need energy. Where does that energy going to come from? Mostly from supernova explosions. And as Tony and Christian told you, most of the time we think a supernova explodes because of neutrinos, right? Besides, there's another interesting way. You don't have to really go out of the star into the interstellar medium to find a cool place. You go to the stellar envelope. The temperature drops pretty quickly, right? That's why lithium, beryllium, boron can survive in the atmosphere of the stars. If you go out far enough in the stellar envelope, you would have these places pretty cool. And you can also imagine that there are carbon, nitrogen, oxygen in these envelopes. And when the supernova explodes, most of the energy gets released in the neutrinos. Neutrinos have typical energies 10 to 20 MeV. It's energetic enough. They are able to knock out particles from carbon, nitrogen, oxygen as well. Yes? This is another cool way to make these guys. Correct? So now you see that the entire periodic table essentially is tied with neutrinos. All right? Okay. We talked about a stage set up by lambda CDM cosmology. We know the players, they are the stars. The question is, how do you become a star? Right? Okay, you have to have charisma. You have to have the right body build and things like that, right? Okay, so pretty much, charisma, forget about it. Body is easy, okay? So all you have to is to have some good nutrition, things like that, right? Okay, so how to become a star? Here's come to, again, the legalistic part and the poetic part, okay? How to be a legal, in this sense, try to understand what is a star. You say, you have to give me the definition. What is a star? I'll say, your poetic mind turns out, oh, star, symbol of stability, symbol of brightness, happiness, light, right? Okay, the legalistic mind, all that crap goes away. All I hear is stability and light. Okay? Stability, that means this thing has been there for a long, long time. Light, that really means that the lawyers are sensitive about the money. That means that somebody is paying the power bill, right? You're emitting light. So you're emitting light, being stable for a long, long time. You integrate, just like Bronson told you. The power limits the computing power because in order to power the computers, now the power bill is millions, right? Think about the sun being radiating like that for 4.5 billion years, right? What's the power bill is going to be like, right? You say, okay, in order to supply that energy, the star must have some interior supply of energy, right? And then you run through the possible sources, who's financing it, some terrorist network, right? They have a nuclear fusion, things like that. All right, okay. You say nuclear fusion has to be in play in order to sustain the stable burning of the sun for such a long time. Then you say you have to have this condition right, that you are able to make nuclei come together, because nuclei, as we talked about, they are positively charged, they repel each other by nature. You have to bring them into each other's neighborhood. You needed to have high temperature, so they're zooming around quite often, so by some chance they might be very near each other, okay? You have to overcome that repulsion somehow. So temperature is a key criteria to assess whether you are able to become a star, because if the temperature in the interior is not right, the nuclei are always stay far apart. They will never come close to ignite the nuclear fusion. All right, how then you do some simple estimate to say how massive or what other characteristics a star has to have in order to ignite the fuel. Okay? So here is the power of physics. You go into this question, as I say, being a poet and being a lawyer, thinking about what the star is, then you say, you figured out it has to be a nuclear fusion problem. Then you say it has to be a temperature problem. Then you have to say what physics then going to determine this temperature, right? Okay, again, you go back to the force. What is a star? Star is essentially a gathering of these baryonic particles. And because so many of them are together, gravity now suddenly becomes important because gravitation is a long-range force, okay? So it just has to talk to everybody inside this influence sphere. And so because it's stable, that already told you that somehow mechanically it has to be stable, yes? So that means gravity try to collapse everything together. In order to resist that, to maintain this mechanical stability, there got to be some pressure force which is pushing it outward. There you go. So it's a mechanical problem. You think about it. In order to make a star stable, you have to balance the gravity with some sort of pressure. Gravity is easy to estimate because you know Newton's law, Gm mp over r. It's better to think about energy rather than the real force, okay? So it's like a 1301, 1302, the introductory freshman physics, you talk about the force. But later on, you immediately know that energy is a much better way of thinking about these things because it's the scalar quantities, right? So you know about perhaps this thing called the Virier theorem. If anything in hydrostatic equilibrium, then the different components of the energy got to be roughly of order, of the same order. Okay, if they are responsible for setting up this equilibrium, right? So, because a star has a fixed number of particles, so the total number of particles you can just divide it out of this energy quantity. You, on the right-hand side, you have the average gravitational energy per particle, right? That's the magnitude. So Gm, m is this cloud, which will become a star. R is the size of the cloud, which will become a star. mp is a proton inside the star. So that's the gravitational energy per particle in this cloud. Now, in this cloud of gas, two forms of energy which will be able to supply the pressure. One is simple gas pressure, right? You have a hot temperature, you know that the pressure goes up. So that's temperature scale, giving you that form of the energy, which is kinetic energy, and simple kinetic energy. The other one is that so far we have been ignoring the electrons, right? Electrons are very important. First of all, they keep the entire gas cloud neutral, right? And the next thing is that it is not very massive. And further, this guy has a peculiar personality. It is a Fermi-Dirac particle, fermion, right? What do fermions do? Fermions have absolute rule of privacy, that you don't come near me, right? So you don't want to be overlapping with me, okay? They don't like to be on top of each other. So that's a real limiting factor because as I told you, somehow in order to make a star, the original cloud has to collapse. As you collapse, you immediately feel the consequences that the electrons will feel the first because you are getting things closer and closer. Yes? So if electrons feel its privacy being invaded, it resists that, right? That's called the degeneracy pressure. That's the form of the pressure which is determining the absolute mass limit for the white dwarf, right? Okay. So you say that, how do I estimate that? Very simple. The privacy is like the modern corporate world. Each lowly employee gets a cubicle. Yes? That's a building, you get a cubicle. So the entire star has a volume which is size r cubed, and you have this many protons, this many electrons, mass divided by the proton, essentially the same number as the number of electrons to keep it neutral. And the little cubicle is d cubed, right? So that's how you divide up. So you get your little cubicle, now you're private. So the Pauli exclusion principle in saying that no two fermions should be in the same cubicle is satisfied. Now suddenly you also understand electrons must be described by quantum mechanics. You get your private space, that means your position now is pretty well defined, right? But the uncertainty principle tells you delta p, delta x has to be greater than something. You're now confined within this cubicle, you're going to bumping around your head like crazy, right? It's pretty much the modern corporate world, right? Okay, so you now have to be bumping around. That motion translates into a pressure. That's the degeneracy pressure. And assuming they are non-relativistic, you can immediately write down that part of the contribution. So these are the two typical forms of the kinetic energy. The electron kinetic energy, when they are squeezed together, and every other particle, basically when they have a temperature, those are the things. Now, these two have to balance the gravity, and that's a very theorem applying to basically some kind of quasi-static cloud. Eventually, it might become a star. You can rewrite this equation in a simple way. It depends on basically the radius of the cloud and the mass of the cloud. And you look at the functional form of this cloud, its temperature reached in the center as a function of radius as this cloud is squeezing with this total mass in the beginning. You find that this curve has a peak. And the peak depends on mass to the 4/3 power. So not every cloud is made equal. Only a certain cloud, when its mass exceeds some threshold, during the collapse stage, its temperatures go above some limit. In order to ignite hydrogen fusion, you need 1 kilovolt, temperature 10 to the 7 degrees. So not every gas cloud can do that. The limit on that is about 1/10 of a solar mass. Anything below 1/10 of a solar mass, you're not a star. So you just shoo them away, all right? Not on the cast. But above 1/10 of a solar mass, you become a star. And this process repeats itself. So once you ignite fusion, you have energy supply, so replenish the energy lost on the surface. The star will be stable for a while, leading some kind of glorious life as a star for a while. Then the central part burns out, hydrogen goes away, right? And then you say, okay, I need more supply, so you need to think about a way to how to burn hydrogen, burn helium. So you need a higher temperature. What you do? If the mass is high enough, you squeeze again, right? Because you haven't reached the maximum temperature able to reach yet. So you squeeze again, so let the radius go smaller, the temperature rises up higher, and then it can start burning helium. But just like for any given mass, there's got to be a corresponding highest temperature you can reach. You know that not every star is able to burn beyond the helium, right? So this thing just is as simple as that, okay? So one slide, essentially your astronomy course for the stellar structure, okay? Now you go further. You say, what about these different stars and how their life will be interesting, right? So let's just look at a bit of detail. So if you look at, you just have a star like the sun, okay? I already said right now the sun is burning protons into helium, and we know that because of solar neutrinos, right? We know that. And after helium, got the dominant form of the matter in the center of the sun will eventually contract and raise the temperature to burn helium into carbon oxygen in the core. And by that time, the temperature obviously decreases as you go outward. If the center is turning helium into carbon oxygen, on the outside the temperature is high enough, you can burn hydrogen to helium. And no, you're still burning helium, but in the center part, you perhaps already finished the helium burning, so you only have the ashes of that, which is carbon oxygen. And on the outer edge of the core, the helium burning into carbon oxygen is still happening. And as you go further out, the temperature drops further. You are only able to burn hydrogen to helium. And further out, obviously, the temperature is so low, nothing happens. You just have some sort of envelope over there. And in the end, what happens is that this kind of a structure where you have an inert core, nothing is happening anymore because the temperature can never rise high enough to burn carbon oxygen in this type of stars. And you have the helium and the hydrogen shells, both are burning to supply energy, and the envelope is extremely convective. And this type of structure, you can do stability analysis, is extremely unstable. This is how the star lost its envelope, mostly through pulsations and winds. And this is how the core, still very hot, gets exposed as a white dwarf, okay? Now, if you look on this scale over here, on the left-hand side scale, this is given in mass coordinates. There's one solar mass star. The core is about half of it, carbon, oxygen, all right? And then the other half gets lost in the winds and the pulsations, things like that. On the right-hand side, you'll notice it's given in the radial coordinate. All that core is about 2% of the sun's radius. And the envelope is essentially the whole volume. And if you read the final radius, it's 225 solar radii. Where is it? 225 solar radii? Okay. The sound radius is 2 light seconds. So that's about 500 light seconds. 500 light seconds, 8.3 minutes. That's here. So we will not see the end of that, but somebody might see that, but they will be gone soon also, right? Okay. So this is how the Earth is going to end inside of the envelope of the sun when it swells up like that. Okay. So you say this is just one solar mass. As you increase the mass, you find out that the temperature you reach maximum in center will never be able to ignite carbon-oxygen burning until you go to about 8 to 10 solar mass or so. Okay? By that time, you imagine that the central part of the core will also be, because you squeeze them more and things like that, you can imagine that the core is also growing fatter and fatter. You are sort of like getting towards this white dwarf limit, 1.4 solar mass also. Okay? By the time you are able to ignite carbon and oxygen near the lower end of this range, 8 to 10 solar mass or so, you actually become so degenerate. The electrons are relativistic, okay? And by that time, you know the instability sets in because relativistic electrons, they are able to capture on the nuclei, such as neon and magnesium and things like that, which you just produce from burning of carbon and oxygen, okay? So when you are supplying the pressure force against the gravity by degenerate electron, but at the same time, the electrons are so degenerate, they immediately get destroyed by the capture. You know it's unstable. The core then collapses. And that's the start mass range of the core collapse supernova. All right? Just when you think you can be a bit more interesting, the kind of interesting become too interesting because suddenly it becomes a supernova. Right. And if you go beyond this 8 to 11 solar mass, there, you're just barely burning carbon, oxygen. Beyond that, the next group will be oxygen, neon, magnesium. And you encounter this electron capture instability, it becomes a supernova that way. If you are above 11 solar mass or so, then the star is massive enough, you actually can stably burn fuel all the way to iron in the center without encountering this electron capture stability on the way. You eventually caught it because when the time comes, there's nothing else to be burned. You just have iron, and the surrounding shell is silicon. Silicon is still being burned into iron. You pile on top of it, you get 1.4 solar mass of this limit again. And remember, at that time, the electrons again become degenerate, and it also is relativistic. The relativistic electrons start to capture on any of these nuclei inside of the iron core, then you going to collapse, right? Okay, so there is the start of the regime of normal supernova, which Tony and Christian talked about. Okay, so that is essentially the life of these players I told you about. And now how about nucleosynthesis? I told you, basically the fusion is essentially the lifeline for these stars. You burn initially from hydrogen to helium, and if you are massive enough, you can continue burn all the way to iron if you are above 11 solar mass or so. This also tells you that somehow you are able to cook elements like this just in association with a star's life, its evolution. Nuclear fusion powers the star, also make these new nuclei. However, I wanted to point out immediately to say that the iron you made on the way to the core collapse in this massive star will not be able to get out, right? Why? Because it collapses, right? Eventually become either a neutron star or a black hole. So this iron is lost, okay? Even part of the silicon layer is lost, okay? The other kind of things which you can get, for example, is the helium, hydrogen, carbon, oxygen, they're far out enough. When the supernova explodes, these things actually would be thrown out, okay? So that part of the stuff you cooked on the way to become a supernova gets thrown out during the explosion. And those are the things you save, like during your lifetime, you're saving. You actually can redistribute them that way. But the iron material you actually make in a supernova comes because the shock wave, when it plows through this envelope, the shock wave again carries lots of energy. It heats up the material very quickly. So you're going to heat silicon into very high temperature and immediately burn that into nickel-56. Okay? Nickel-56 decays and then becomes cobalt-56 and then becomes iron. That's the iron we see in supernova. All right? That's how it gets out. And you say that's not even a small fraction, just only a small fraction of the periodic table, right? Iron has 26 protons, right? The entire periodic table extends to lead and even beyond. So like a proton number 80 in the 90s, and things like that. So you have a lot of elements not explained yet. How are you going to go beyond iron? Okay, knowing that the stars basically, in the simple fusion way, can only process to this point of iron. You say, well, at that point, you really worry about the efficiency problem. Okay, already take 10 million years to go all the way there, right? In a massive star. If you wanted to do very kind of an inefficient process, perhaps you won't even be able to explain what's already out there in terms of the elements beyond iron. So you need something more efficient. More efficient, you want to get rid of one thing, which is that charged particles repel each other. Okay, how about we just get rid of one of the charged particle? We replace it with a neutron. Neutron is free of charge. So neutrons can be captured more efficiently. But you are stuck with a problem because neutrons, you cannot inherit from somebody. It decays in 15 minutes, right? So in order to do this kind of process by capturing neutrons in order to make heavier elements, you must make your neutrons in your workshop, right? And the only way to make neutrons is weak interaction. Weak interaction with ions and neutrinos. One kind of neutrinos. And if you say that neutrinos only talk weakly, but if you have zillions of them, many of them work together, you still can perhaps supply enough of neutrons, right? So this is why core collapse supernova is such an important place for thinking about making elements far beyond iron, because it likely can utilize the source of neutrinos to do weak interaction in the best way, okay? All right, so sort of I come up to the end of this sort of introduction. If you want now have the stage, you have the storyline. Neutrinos is important in the origin of the elements. You still have to let the general public, take some kind of a pleasure in actually knowing about this. So you have to be a bit cartoonish here. You can think about it in two ways. Okay, to the public, this is basically an interesting story that stars born out of clouds, and they come in different varieties and kinds. And smaller stars, they eventually eject the envelope in planetary nebulae and leave behind white dwarfs, right? But if you're a massive star, you blow up as supernova, and you leave behind neutron stars and black holes. And whatever the material ejected from the star goes back to this stellar nursery, right? And it goes back to the sort of like the breeding ground for new generation of stars. And this kind of thing is a cyclic thing. And then you think about it in a computational way, it's a subroutine, right? So you say this is the initial conditions for main stars, and you have a mass function telling you that, okay, how many 1 solar mass stars you're going to make, how many 10 solar mass stars you're going to make, et cetera, et cetera. Then each individual star follows its life trajectory. And in the end, they blow up and go back to this stellar nursery again. And so it just repeats, just like a do loop, right? Many do loops later, some lucky accident, we have the solar system. And voila, life arises from the ashes. That's the grand finale, right? Okay. So I think I had enough of this general introduction, and I think perhaps it's best to, how long do I have? When did we start?
10 minutes after the hour.
So okay, I will just go a bit then beyond that, all right? So this is basically the general story. And as we see that I kept on emphasizing, the nucleosynthesis part has a lot to do with neutrinos. Now the next part, I will again try to play the lawyer part. See, everything we do in science, the ultimate judge is nature, Mother Nature, right? First of all, you want to cheat a little bit. You want to already know what Mother Nature is already telling you, so you don't have to scratch your head and thinking about how to go about things. You say supernova has a lot to do with nucleosynthesis. How do you know that? How do you know that? Because of the observations. Mother Nature already revealed it to us. And this is essentially a figure about the optical luminosity, more or less. In here is a vertical axis, essentially the luminosity in millions of solar luminosity. Think about a million sun, okay? So this is like that, okay? And this is the days after the explosion. In one of the case, supernova 1987A, okay? And as you can see, it blows up, I think, near the end of February 1987. And by May 20th, it reaches its maximum brightness. It's about 200 million suns, okay? And that supernova is not in our Milky Way, it's in our suburb, basically in Large Magellanic Cloud, which is 50 kiloparsec away, okay? So this is a very bright event, and that shows you how powerful a supernova is. But as you remember, this optical display is really a sideshow to the supernova process. Most of the energy comes out in neutrinos, and here's actually where the neutrinos is. Here is a broken up scale over here. And the scale over here is 3 times 10 to the 13 million solar luminosity in neutrinos, okay? And that is a burst lasts 10 seconds, which you already seen from the previous talks about supernova neutrinos, okay? And if you notice how the supernova is going on, it really goes on like this. I mean, light just, it brightens up. That's why you know it's a supernova. So it reaches the maximum, then it decays. And then if you notice this long tail of the decay, it has a very interesting mathematical structure. You can actually fit an exponential decay law to it, all right? I will show you in bit detail later. But let me also talk about here why the supernova becomes so bright at that point. The reason is you're seeing it in optical, so it's got to be some kind of optical emission, right? Where that optical emission energy come from? In the very early days, you think about the supernova shock wave delivers kinetic energy into the envelope, and being a shock wave, it has energy, it's very hot. And when things get hot, the first to think about is dissociation. In the envelope, say initially you might just have a hydrogen in the atomic form. There's an electron, there is a proton. When it's heat up above 10 to the 4 degrees, the first thing happens is the hydrogen gets dissociated. The electron gets dissociated away from the proton. And then, because it's an explosion, things moves out, it expands. When it expands, it cools down. When it cools down, temperature drops, the electron go back to the proton. What happens then? The 13.6 eV photon comes out, but because it's still lots of envelope material on there, it sort of randomly walk around a little bit, gets thermalized, and eventually it appears in optical, which is around an EV sort of thing. So 13 EV photon degrades into about 10 of these photons, and that powers this optical display. Okay? That is essentially the reason why we know it's a type 2 supernova, because type 2 supernova has hydrogen in it. Okay? And then the rest of it is that that process can only last that long because it keep on expanding. The shock wave is no longer supply energy by heating this dissociation anymore, and you still are very bright. You've got to be another energy source, right? Another energy source. This is the direct evidence about the newly synthesized nuclei in the supernova process itself. Remember I told you that as the shock wave go out from the iron core, the first thing it encounters is the silicon layer, right? Silicon is being burned into iron, but it's still lots of silicon there. The shock wave is so hot there, it immediately burns silicon into nickel 56. Silicon, 14 protons, 14 neutrons. Basically, mass number is 28. 2 of the silicon, it's just a nickel 56. Nickel 56 is radioactive. It first decays into cobalt 56. Then cobalt 56 decays with a half-life about 2 months or so, 77 days. And it doesn't decay to the ground state. It decays to the excited states. The excited states then de-excite by emitting gamma rays. Now, gamma rays, again, in this environment, they cannot escape immediately. It's sort of like gets thermalized again. So that's your heat source for the long term. But you know that this guy decays with a very specific lifetime. So if that's the energy source, the luminosity you see in the photons got follow this decay law for the energy supply. And this is a semi-log plot. So the longitudinal, I mean, this vertical line is a logarithmic thing about the luminosity, and the horizontal line is the time axis. Exponential decay on the semi-log plot just becomes a simple straight line. You can read off from the slope, and you know that's the decay lifetime of cobalt-56. All right? And you say that now I can go figure out what other things the shockwave might be making. Because in addition to processing silicon-28 into nickel-56, and it eventually becomes cobalt, you can also make other things, cobalt-57, titanium-44, there's also sodium and things like that. Each of these guys are radioactive, coming along with its own lifetime. And if you know from your model, in order to make, say, this much cobalt to power this part of the light curve, how much other things are going to come along with it, then you can immediately find out a composite light curve eventually the supernova should show you. And as you can see that indeed, if you put up all these guys, amount you are making it with, and also the lifetime of these things, the sum of this thing, which comes up to be more or less like the solid curve, and compared with observed data, they're pretty good, right? And this, by the way, essentially is similar to how in the early days radioactivity was discovered. At that time, nobody knew what exactly this thing is. The only thing they found out is that the decay follows an exponential law. And if you have a different decay rate, it's got to be a different radioactive nucleus. Yes? So by that time, the only thing they have is a Geiger counter. So you just have a piece of material, you hope some radioactivity is in there, and you isolate them, and you just listen to the click rate. If you suddenly find out it's a different click rate, you say, I discovered a new radioactive nucleus. This is how Madame Curie worked her way up in this way. All right? The same thing we now doing it in the supernova. All right. Now you actually can compile all of this information. One is that from the light curve, I can infer how much nickel mass was made because of the decay rate and the power of the luminosity. And because of all the interesting way the initial gamma ray was thermalized and put that into the energy source for the visible photon, it deals with the envelope structure of the star. You can look at the detailed evolution of the light curve, also infer what is the main sequence mass of this supernova. So from that light curve observation, you suddenly have a lot of data. Tony showed part of that thing to you. And you can obviously also look at the spectroscopy. If things are moving out, they have Doppler shifts. Okay, you can figure out how fast things are moving, so you figure out the kinetic energy for the supernova. So you immediately get these interesting plots that as a function of main sequence mass, you find out that the explosion energy in terms of the kinetic motion of the debris at infinity clusters around 10 to the 51, which is called 1 beta, right? 10 to the 51 erg, that unit. And this is only for a limited range, around the 15 solar mass or so. But once you are in the regime of 20 solar mass and above, you suddenly go into two branches. One branch, this explosion energy could be tens of times higher. And for the lack of a better name, people call it the hypernovae, right? And then there's likewise in more or less the same mass range, but you find some very wimpy explosions. And those are, for the lack of even not so good name, they call it the faint supernova, right? And in terms of the nickel mass, same way. You find out that the hypernovae ones, they can make a lot more iron, whereas the faint one obviously have very little iron to give you, all right? And so to sort of orient you in a sort of like this organizing game about these different varieties of supernova, you can think about it in this way. The normal kind, which Tony is able to more or less expose pretty surely, as in the mass range about 12 to 25 solar mass or so. The hypernovae and the faint supernova is anything above it, because it's not so easy to think about how to really robustly explode them. And observationally show you that their fate actually is quite different for different situations. And you say, that's poetic. Show me some loyalistic thinking here. Why there should be a mechanism distinguishing this kind of progenitor mass from the other one? so that I see different explosion energy, I see different kind of nucleosynthesis products. Well, Tony told you, this is his famous figure, repeated about 10 times at least already. So here, you have a neutrino heating. And the neutrino heating typically works in the low mass range, simply because the envelope, which sort of during the collapse will keep on raining down, and that provides like the headwind for you. The explosion powered by neutrinos is not that powerful enough to overcome a lot of that headwind, right? And so that works in those situations. But suppose you are much more massive. The headwind is so strong, it overpowers the neutrino. What is going to happen? If you think about it, material, if you think about it in a spherical way, okay, angular momentum conservation immediately tell you everything follows on the radial trajectory. If it comes in, nothing stopping it, it all piles up in the center, right? So that's essentially, if you shoot say, 2 or 3 solar mass in the center, you become a black hole. That's the end. Okay, so then you know that actually it's not the case. If material comes with some angular momentum, which is obviously ubiquitous in any kind of a stellar object, we know the sun rotates. Everything rotates with an angular momentum. Angular momentum conservation happens even during the collapse. So you have to preserve that angular momentum. You don't go on a radial trajectory. You have to preserve it. You go like this. You end up in a disk. That's called accretion disk. And when you have accretion disk, at least ample evidence from observations shows you always have a jet. And the more angular momentum you have, the more kind of a powerful jet you get. You punch through the rest of the supernova envelope this way. That's a hypernova. And if you are a pretty wimpy rotator, the jet is not that powerful. You get a wimpy explosion. That's your faint supernova, right? And so this is essentially half poetic picture. We do have observation evidence telling you if you have a jet, always comes out in bipolar way, right? So if you happen to looking down towards the jet, some spectral line, will only have a single shift. If you're on this side, you just see some rest wavelengths shifted because of the Doppler shift. But if you happen to look on the sideways, you look 2 jet, one going up, the other one going down, the same spectral line at rest now gets Doppler shifted in 2 different directions. So you get a bifurcation of the spectral line. And this is one particular hypernovae. You actually saw that, okay? So I think I should stop here, and I just continue the more interesting discussion about the nucleosynthesis tomorrow. So you now know the things. Neutrinos have a lot to do with supernova nucleosynthesis, any other kind of nucleosynthesis. And supernova is not a simple object. It has a variety of things. And that makes life interesting. And that also makes the life of the stars interesting, but it also makes the life of the theorists studying the life of stars interesting, right? Now we have all this variety of interesting to explain.